Hello and welcome to the Formula SAE Power Senior Design Expo. My name is Dawson Pauley and I'm joined by Spencer Nichols, Michael McCrary, Jeffrey Cecil, Nate Ruscialelli, and Aaron Dubiansky.
Our completed work includes mechanical modifications such as fabricating a new engine stand in order for a new engine to mate up to the dyno, and measuring our valve train for accurate simulation design. Also, our electrical modifications, we've changed connectors such as the crank sensor, the coolant sensor, and the starter relay. And we have fixed our engine synchronization issue and started using the secondary map sensor.
For GT power validation, the GT power simulation was modified to reflect actual trends. Similar trends shown with some variance with an average percent error of 2.1%. Looking at both the graphs, we got our base simulation that we got through GT power, and then we got our average tested volumetric efficiency from the data we got from running the engine on the dyno.
Once we had validated our simulation, we used the design optimization feature in GT Power to achieve our target of maximizing volumetric efficiency between 3,500 and 8,500 RPM. Throughout the GT Power optimization, we were able to achieve a much higher peak volumetric efficiency and higher volumetric efficiency across the board. We achieved approximately 99% between 5,500 RPM and 7,000 RPM, although it still decreased abruptly after 7,500 RPM due to choked flow through the intake restrictor.
Here are some images of the CAD models for our design. From left to right, starting at the top, we have the profile of our intake restrictor, our plenum, the throttle body and restrictor assembly, the intake runner, and finally an exploded view of our exhaust system assembly.
For our CFD progress, we managed to create a volume mesh of the fluid moving through the restrictor, in which was included a prism layer for improved boundary layer accuracy, and a trim mesh was used for the surface of the restrictor. The following solvers were used for the physics calculations: ideal gas, turbulent, coupled flow, 3D, steady flow, K epsilon turbulence, and Reynolds averaged Navier-Stokes. Here the CFD results are visualized. The inversely related pressure and velocity gradients expected of a fluid moving through a venturi were observed, in that the highest velocity and lowest pressure occurred at the throat.
And that concludes our presentation. Thanks for watching.